this space locally looks like this cross this. So in particular, it could actually be the global product. That's also an example. But it need not be globally a product. It's just locally this cross this. Now, if you're in the setting of smooth manifolds, everything will be smooth. So this is a smooth map, typically a smooth subversion, all of that. And typical fiber is homeomorphic to S3. I'm saying every fiber is canonically identified to S3. During the topological setting, these are all computer maps and these are all. That's all. We have seen many examples and we will introduce them. But this is what we have studied. And so here, he was constructing a Morse function right. Not for all of these, but for certain. Okay. But if we ignore this for a moment, let's go back to what we know. So, well, whatever this thing is, it turns out there is a whole bunch of them. We still look at the height function here, right? Let's call this map phi. So this data is phi, 7, this 4, fiber bundle with fiber S3. So a fiber, if you haven't seen this word used before, fiber simply means you choose a point, look at its free. So any two free images will be homomorphic because they are locally the same. They are all homomorphic to fibers at some point. So you can look at the usual height function on S4 and then pre-compose it with phi. So if you look at this function, what can you see about this function? This is which way does the phi? Phi, right? So if everything was smooth, this was smooth, this is obviously smooth, this is also a smooth function. For a smooth 7 manifold, it lands in R. But can this be a Morse function? Just think about what it could be, right? If it's a Morse function, one of the first things we do is the critical point has to be isolated. But in this case, what are the critical points? Or is the critical set more than single set isolated points? So because this being a fiber bundle means what it means. If you take one copy of S3 living over a point P, all of that under point is close to a point. Right? That's precisely what a fiber is. So if you look at the critical point of the height function, just to North Pole and South Pole. So the S3 is living over those 2 points are all will be part of the critical set. Because that simply just goes to a point. Right? So this is just a check. Look at this. This is my inverse of 0, 0, 0, 1. In fact, that's it. This is essentially, you only have integral points of this function is going to be 2 S3. One which is living over the spin edge of the North Pole, which is one of the critical points of X, and the other one is going to be the spin edge of the South Pole. So this is the South Pole. So anyway, spin edge over the 2 poles. The point is this is one copy of S3. This is another copy of S3, and clearly they are not isolated. So what you get is not too bad. It's not a Morse function, but it's still a nice function in the sense that the critical set is a disjoint union of 2 submanifolds. And you might want to say, okay, what is so nice about it? Well, you might want to have a version of the Morse method. But now you cannot say that the Hessian is non-degenerate in all possible directions, because along the submanifold this function is constant. Because it simply collapses there. So along the tangent, so if you are at a point in the submanifold, if you are moving in the submanifold inside M7, the Hessian will simply vanish, because the function doesn't. So you can only ask for the Hessian of this function to be non-degenerate in directions normal to the submanifold. So you could imagine this picture like this. So you have one S3, and just pretend that this is this. This is, let's say, S3 plus. Plus, this is your you have a function, not a Morse function. And these are the two critical submanifolds. And what you want, if you're moving along these directions at a point P in here, the Hessian is not going to capture anything. But if you're moving in directions normal to this submanifold, you want the Hessian to be normal. So I'll make that precise. So let's see this example here. I'll do one more example, which is of a similar kind. But all I'm saying is that these functions are also nice. If you have a fiber bundle of any kind, you choose a Morse function here. Such a function will not be Morse. So whatever critical points this function has, the pre-images of those critical points are going to be critical submanifolds of the composed point. But they will be nice in the sense that if you look at this function and its Hessian in the direction normal to the critical set, they will behave nicely. And that's essentially what we want if you want to exploit a version of Morse level. Because Morse level tells you what to do in direction. See, for the Morse level, the critical set was a point. So for a point, the tangent space is just zero. The normal space is everything. And in every direction you want either a bunch of plus or a bunch of plus. Here you want to do the same thing, except you cannot do anything along the submanifold, because along the submanifold is something in the point. But in the normal direction, you want the same kind of a local structure. Yeah. Other example you already see for us. Again, the height function. And this we saw had two critical submanifolds, right? Sorry, this one. And there was one at the bottom. So it's just the torus kept on the floor. So we have this on the top, and then something like this. Right? So this yellow thing is supposed to be at the bottom. So you have two critical sets. So CR H is the disjoint of this one, the orange circle and the yellow. And this again is also not a Morse function, but a nice function. But you should see what this is, right? So does this match with this kind of a framework? It's right? Because you simply take the height function on the S1 and then you are taking this to be the product one, S1 plus S1. It's literally a subcase of this if you ignore all the 7 elements. So you simply say look at the height function on S1, it has two critical points. You now take S1 cross S1. So both points now constitute a whole bunch of circles. This is also not a. But if you don't like exotic examples like this, you could do any other. Let me try to see the plan. So we did this one also, but this is not that form. This was X, Y, Z. This is again a different example. It's not of the form that this is a fiber document because it's a space of its own. But here, you check, at least some of you are considering that this thing was the equator along with S0. I'm going to call it S0 because from a topologist perspective, S0 is simply the zero sphere. S1 is the one sphere, which is the circle. So S0 is the zero sphere. So what is the zero sphere? It's a unit sphere, 0 plus 1. In the real line, the zero sphere is just plus 1 and minus 1. So it's just 2 points. These 2 points are precisely in this case the North Pole and the South Pole. So it's like a doubling map. So the equator becomes a critical set, and then you already have the original critical. Okay. So I mean, you are seeing two kinds of examples. One where this is a generalization of a Morse function where the critical set are submanifolds of the same dimension. Same thing here. Here the critical sets are submanifolds, not necessarily of the same. Okay, so now I think we can define what is a Morse spot function. The Morse spot function is a generalization of Morse function which subsumes zero. And you might say, okay, why do we need to go to Morse spot functions? Well, Morse functions are nice, but quite often you will encounter such functions in practice or in kind of deformations. And then you can still get a Morse function out of it. But The point is, you might encounter more smart functions more often than more functions in practice, not as there. Yeah. So, slogan, everything here is what do you want? You want HTML